So good morning and welcome back. Today we continue our study of the special linear group SL2C, so the relativistic spin group, and in particular of its Lie algebra. And today we would like to conduct the analysis that we did in theory in the second previous lecture. We'd like to do it for the example of the special linear group and its algebra, namely the construction of the Dynkin diagram. So last time we arrived at the point that we constructed from the coordinate-induced tangent vectors d by dxi at the identity. So those are elements of the tangent space at the identity element of the special linear group SL2C. So this is this guy. We constructed from these, and where I runs from 1 to 3, the left invariant vector fields on all of SL2C by virtue of taking a left translation to a point ABCD and the push forward thereof. So we apply this to the first, second, and third tangent vector at the identity, and we found already last time that this gives rise to the following vector field, left invariant vector field on SL2C, A minus B C 0 A 0 B 0, and this is D, but in the coordinate chart chosen, the first coordinate chart we constructed, this is 1 plus BC over A. But this is just a symmetry of numbers where M is the row and I indicates the column. And this is to be multiplied by D by dxi, but now at the position, at the point ABCD of the underlying SL2C manifold. So from a tangent vector at a point, from 3 tangent vector at the point, we construct three left invariant vector fields of this form. So why did we do this? Well, we're working towards the following. So we have the theorem that taking the tangent space of some Lie group at some point, that tangent space can be equipped with a Lie bracket, which here, for distinction from the differential geometric Lie bracket, I indicate by this double bracket symbol, that as a Lie algebra, so not only as a vector space, but also as a Lie algebra, this is isomorphic to the set of left invariant vector fields L of G on a Lie group equipped, or which inherits. So this set is certainly a subset of all the vector fields on the Lie group, so a subset of the section of the tangent bundle of the Lie group, which is an infinite dimensional vector space over R or C, whereas this is as we saw, a finite dimensional vector space. But this L of G, the set of left invariant vector fields, inherits a bracket from the differential geometric Lie bracket here, which is this one. And it's, of course, much more handy to deal with the tangent space at the identity and to equip it with a bracket in order to mirror this behavior here. But here, this bracket, as I said, we get for free because it's the differential geometric Lie bracket, whereas on this side, this bracket we need to induce from over there. And so, of course, how that works in this context is that we define the bracket here, d by dxi, which is supposed to be a vector at the identity, and d by dxj, also a vector at the identity, with respect to, say, the first coordinate chart. And we define this bracket by its action on the function to be given by, now here we have the differential geometric Lie bracket as indicated above. We push forward the d by dxi vector to a point A, B, C, D in the manifold. So if we are really picky, we indicate here that this is a vector at the identity that's being pushed forward. And again, L, A, B, C, D, push forward of d by dxj at the identity here. It's like this. And now the differential geometric Lie bracket closes. We decided to define this by action on an arbitrary function f, which is a smooth function on SL2C. Okay. But now this, of course, yields the derivative of f at the identity. This yields the derivative of f everywhere. Last time I indicated that one possibility to remedy this is that before we act on f, we actually have this pushed the opposite direction. But an even easier way to obtain the relevant vector at the identity is to evaluate the whole guy here, so this bracket, to evaluate it at the identity before we apply it to the function f. So we get a vector at the identity. And in order, so this fully defines this Lie bracket on this tangent space, but in order to study the corresponding structure here, we definitely need to calculate the right-hand side. So unfortunately at this point there's no better method than to just carry through the calculation. So we need to calculate the following three brackets. We need to calculate, okay, so yeah, need to calculate the following brackets. D by dA at the identity with d by dB at the identity, where I now use the fact that in the coordinates ABC, the first coordinate chart, of course, the x1 stands for A, the x2 stands for B, the x3 stands for C. It's convenient to label it here in the general formula like this, but once we start calculating these brackets, it's easier or more transparent to label them by their actual names, these coordinates. So then we also calculate d by dA, d by dC, all at the identity. I don't need to indicate this again. And d by dB, d by dC. Well, in order not to get confused, let me write id here. So this is supposed to indicate the same identity element. Okay, so how do we evaluate this bracket? Well, by action on function and by using this definition, but now we can plug in what we learned up there. So we take the differential geometric Lie bracket and we have to look at what is the push forward of the first tangent vector with respect to these coordinates. So that's I is 1. So, but that's the column, so the row here, oh, there's a mistake, so this is an M here, of course, so there's a summation convention going down here. So the column is being fixed to the first column, and the M is running, so it's A d by dA, A d by dA, minus B d by dB, plus C d by dC, comma, so that's the first one. The second, the push forward of the second vector field, it's the same game, obviously played with the second row, but that's much simpler. That's A d by dB, close bracket, acting on a function. So let's first write down all the brackets. So this is again the A vector field. So d by dA minus B d by dB plus C d by dC, but now acting on the third, and that's B d by dA, B d by dA, and plus 1 plus BC over A d by dC, close differential geometric Lie bracket, acting on F. And as we said, we want to evaluate this bracket at the identity before we let it act on the function. Okay, so we have this. And finally, the third bracket is given by the second vector field. Well, we already wrote this down here. That's the simple one, A d by dB. And the third one, this is that one, B d by dA plus 1 plus BC over A d by dC, close bracket, evaluated at the identity on F. So that's the task at hand. And I remind you that these are not the naive partial derivatives, but they're the differential geometric derivatives referring to a chart. You remember our convention here and our notation. Now, okay, let's start with the third bracket because it's the simplest one, and we'll learn a lesson there, which in principle we already know, but it's good to see this in practice. Let's evaluate this bracket. So this bracket, of course, is evaluated as follows. I let this field act on F, and then I let this vector field act on the result, minus the other way around. First this acts on F, and then this vector field acts on the result. So let's write this down once in full to not get confused. A d by dB of B d by dA plus 1 plus BC over A d by dC, acting on F, so I can immediately write the F here, F, minus the other way around is B d by dA plus 1 plus BC over A d by dC, and this acts on A d by dB on F. Yes, that's right. So that's this guy. So now let's do this action properly. So now you see d by dB acts on this guy, but that's a product rule needed because the b acts on the first factor and on this one. So by the product rule, this is d by dB on b. Already looks like 1. It is 1, but you see it's not the partial derivative, so you have to do 1 or 2 intermediate steps, but that's how this always works out. So this is 1 times, and then all that's left is d by dA f. But now because of the product rule, there's an extra term. There's the term a, you keep the b, and you let this derivative act here. So you get a second derivative, d2 dB dA acting on f. So that's the action here. Now we continue. This is plus. Now this acts on this. Same game. There's a b in here. So you have to take this derivative. The a goes against this a. We derive with respect to b. So what remains is a c. That's right. A c, and then d by dc f. But now product rule, we have a term 1 plus bc over a times a from here. And now the second derivative, del 2, del b, del c acting on f. So that's the first part of the bracket. And here the same procedure, of course, applies. It's the minus from here. Then you have the b. D by dA is 1, so you get d by dB f. But product rule instructs you to have minus ba second derivative d by dA d by dB on the function f. And then the final term here, minus the derivative of c. Now, you don't need the product rule here because the first factor doesn't contain a c, so you can pull it out immediately. So that's minus 1 plus bc. The a here cancels, and then del 2, del c, del b acting on f. Okay. So now looking at this, we have an expectation, and a justified expectation, that is that the Lie bracket of two vector fields is a vector field. So the vector field can, of course, always be expanded in the basis, so in a d by dA, d by dB, and d by dC. But here, there's some other guys appearing. They're the second derivatives appearing. There, and there. And these have nothing to do with an expansion of a vector field, and they better be absent. Well, let's check this. So there's the derivative with respect to BA, but there's also the one with respect to AB. Now, despite this being not directly the partial derivatives, it of course very quickly reduces to the partial derivatives of the function composed with the inverse chart map, and the Schwarz lemma that allows you to exchange the partials also applies here, because our manifold is sufficiently often continuously differentiable. And you see you have plus AB times this minus AB times this. This guy cancels against that guy. Now what about the d by dB, d by dC? Well, also that one has its counterpart here, the factors. So here the a's cancel, of course, first. You have the plus, you have the minus. This one cancels against that one. And it must. It's not a surprise. It's more like a check on our algebra here. And what remains is the following vector field. And we decided, I didn't indicate this here in these lines, but we decided to evaluate the vector field at the identity. So, but let's first write down the full vector field. It's A d by dA. Then we keep the minus B d by dB. And we have the plus C d by dC on F. But we want to evaluate this at 1, 0, 0, 1, acting on F. And you know that the coordinates in the first chart we chose of 1, 0, 0, 1 is ABC. So it's 1, 0, 0. So only A is non-zero. A is 1. That's this guy. And those two guys are gone. So we get d by dA at the identity on F. Aha. Okay, so we evaluated this bracket, and so maybe we denote this here. So this bracket, so this is the equation, the equal sign that comes from here. This is simply d by dA at the identity acting on F. So if you forget about the F, because valid for any F, you have that the B vector, the vector in direction B at the identity, the vector at the in the direction C at the identity, they have the Lie bracket that leads to the d by dA, to the first vector in this coordinate-induced basis at the identity. So this is how this calculation works. And in evaluation of these two Lie brackets, we will now simply immediately drop the second derivative terms, because we know they will cancel, they must cancel, and that makes the calculation more transparent and a little bit simpler. But I also indicate, I show you, or I want to emphasize that we got here exactly what we wanted. We take the bracket between two elements of the tangent space at the identity, and we get a vector at the identity. Okay, that's what it is. But yeah, okay. So now let's evaluate the other two brackets. So maybe we keep this here so you can see this. So well, let's do this here. Okay, so evaluation of this bracket, that's the second bracket, works as follows. So we act with the A on this one. So we have A d by dA that sees this one. So we wanted to drop the second derivatives, but the second derivative is also only if this derivative acts on this one. So in this case, we have an A, and in fact, it acts non-trivially on this factor, so we get a first derivative, namely this one, A d by dB. Next one, minus B acts here, doesn't act trivially. It only acts trivially on the first factor. That means it would produce a second derivative. We drop that one. Same here. This d by dC acts trivially on that first factor, so it would produce a second derivative. We drop that. That's it on F. Now the bracket the other way around, minus. Now A d by dB acts on these guys, but of course the d by dB only acts non-trivially on that factor, so the other ones would produce second derivatives, which we decided to drop. That's the minus from the definition of the bracket. That's the minus from here, yields a plus. The A comes from here, non-trivial action gives a 1, and we remain with d by db on f. And that's already it. So we need to evaluate this vector field at the identity first. That's a equals 1, b and c equals 0. So this is simply 2 times d by db at the identity acting on f. It's that quick. Although the bracket is more complicated, we achieved this by immediately dropping the second derivatives. So let me also denote here in similar fashion the result. This is 2 times d by db at the identity. And because we acted on f there, let me act on f here. All right. So now let's take this bracket here. So okay, so this is done. Okay, so now let's take this last bracket here. So nothing to do with this. Equal. Now we act here. Okay, same game. A d by dA. We need to be a little organized because there are more terms. But let's always take this term and let it act on everything back there. A d by dA. On what can it act non-trivially? Well, if the factor contains an a. This doesn't, but this one does. So it's a times, now we act on here, the derivatives, of course, minus 1 over a squared, 1 plus bc. That's this non-trivial action, and what remains is the d by dc on f. There will be an extra term from the product rule, but it's a second derivative. We can drop it. So we dealt with this one. Now this one here acts on everything that has a b that's both factors. So minus b times d by db yields 1, d by dA acting on f from here. Minus b times acts on this by derivative with respect to b yields a c over a. B is c over a, that's right. And then d by dc acting on f. That's these two terms. Okay. Now, next term. This one acts on everything that has a c in the factor. This one doesn't, but this one does. It's plus c times. C is b over a. B over a. And the derivative that remains is d by dc on f. Okay, so that's the first part of the bracket. Now we have to have a minus sign and do the second part. So maybe to be safe, we open a bracket here and keep the signs that are there. So now this one, let's have it act on each of these. So b d by dA can non-trivially act only on this guy. So you get a b times 1 times d by dAf. So here the a goes, and that's the dA from here. That's right. So and on the others, it only acts trivially. So now let's take this gentleman here. It's 1 plus bc over a. Can non-trivially act only on this one. So you get a d by dc of f. That's it. Okay, so the brackets are not really needed. We have this under control. There's a minus sign here as well. Okay, so same game as before. We now evaluate. We could simplify first or evaluate first. Let's evaluate immediately. We evaluate this at the identity. So let's indicate this here. At the identity, we evaluate identity in these coordinates is a equals 1, b equals c equals 0. So this is 1 times 1 plus 0 over 1. This is a minus d by dc f. So this one is 0 times, 0 times, 0 times. And always the a is 1. So that's well defined. This is 0 times, and this is 1 minus. It's another minus. 1 plus 0 over 1 d by dc is d by dc f is minus 2 d by dc acting on f. So at the identity, of course, because that's what where we evaluate. So we have our third bracket. Here it was plus 2. Now here it's minus 2 d by dc at the identity. Okay, so we achieved finally in defining the Lie brackets in the tangent space at the identity of the SL2C group. And that's the full calculation. And that is what, in principle, you have to do every time you start with a Lie group and wish to derive the corresponding Lie algebra in its full glory. So for future reference, let's repeat what we found. And I now use the short notation x1 for the first vector d by dA at the identity, and x2 as d by dB at the identity. And this we found is 2 times x2, and x1, x2, x3. We found is minus 2 x3, and finally x2 and x3 we found to be simply x1. So where from now on we have xi equals d by dxi at the identity, and obviously the Lie algebra is spanned by this because that's the tangent space. So you see the Lie algebra of SL2C is just these abstract tangent space vectors, has nothing to do with 2 by 2 traceless matrices or so. Of course, there are a representation of this algebra. We'll come to representations later, but this is the definition we had. Okay. So now, once we have this algebra, the first thing we can read off are its structure coefficients, or structure constants. Structure constants of SL2C in this spaces. If we had chosen different coordinates on the Lie group, we had a different coordinate-induced spaces in the tangent space, and you'd get different structure constants. So the structure constants depend on the basis, but of course we know how to transform between various spaces. So in fact, it's enough to say in some bases they look like this. You can get another one. So the structure constants, of course, you remember, you read off by having xi, xj, and you know that the result must be again an element in the tangent space at the identity, and because the x1, x2, x3 constitute a basis, there must be a way to expand the result in that basis. Now, you need expansion coefficients ck, but they will be different for various ij's. And because this bracket, of course, inherits its antisymmetry and Jacobi identity from the differential geometric Lie bracket, in particular, this guy is antisymmetric down here. So I can write without changing anything, I can write this weighted antisymmetrization bracket, but I don't have to. Maybe it's clearer here to say that this is, of course, minus ck ji xk by construction. Okay, and these guys are the structure coefficients, and because we're dealing with a complex Lie algebra, these are simply a collection of complex numbers, and I, j, k run over the labels of the basis vectors. Those are the structure constants, and so we saw that there's an important object called the killing form of a Lie algebra, in this case of SL2, C. That guy was abstractly given by k of an A and a B being elements in the tangent space at the identity in this case, and that was given as the trace of the adjoint of A composed with the adjoint of B. But now, since we're dealing here anyway with a particular basis, we can also represent the components of the killing form. We calculated that last time, I think. And there we found that you need to take the structure coefficients twice. They come with such an index structure. So, of course, one would never be enough because it has 3 indices. This has 2. By no contraction would you make out of 3 indices 2. But if you have these 6 indices, you can. And carefully taking care to not unduly exchange lower indices, because the whole thing is anti-symmetric in there. We have the ij here, and the other 2 are being summed over, but you can only sum this upper m, say, with this lower m, and this lower n with this upper n. That's the only possibility. And be careful, if you start exchanging here without doing the same here, you get an overall minus sign, which doesn't do any harm as long as you're aware of it. Now, obviously, it's quickly seen that if you take into account that here you have the complex conjugation between these coefficients, that in fact you can, of course, exchange these 2 numbers times CMIN. And after you did that, you're fully free to rename, to relabel these dummy indices m into n, if at the same time you relabel the n's into m's. They're just dummy indices. But now, carefully looking at this and taking into account this definition, this is, of course, kji. And of course, the killing form is symmetric. We indicated this before. Now, why are we interested in the killing form of a Lie algebra? Well, one thing you can decide is that the semi-simplicity of the Lie algebra. And in fact, the claim is that SL2, C, our relativistic spin algebra, is semi-simple as a Lie algebra. Is semi-simple. Now, how do we check this? Well, we apply Cartan's criterion. Cartan's criterion, and that was you've got to check, this is equivalent to the killing form being non-degenerate. Degenerate. And that, of course, means expressed in these terms that if you naively take the square matrix defined by it, and you naively take the determinant. I say naively because you can only take, strictly speaking, the determinant of an endomorphism, and this is a bilinear form. Well, this is a density, whatnot. But anyway, you do this naively, and it better be not 0. If it's not 0, then K is non-degenerate, and yeah, that's right. It's non-degenerate, and that does the trick. Okay, so we need to calculate this guy. Now, this is a lot of work, and I'll only show you this for some sample components. So obviously you have to, well, it's a symmetric matrix, so it's 3 by 3 symmetric. So you have to calculate these 3 guys, and these 3 guys, and these 3 are determinants. You have 1, 2, 3, 4, 6 numbers you've got to calculate. Well, I show you for the first entry, K11. Let's calculate this, and you can calculate the others on your own. What is K11? Well, it's just a disciplined execution of the Einstein summation convention. You have a summation here, you have a summation here. The best advice is to do this step by step. So plug in the ij, so you have a C1 mn, C1 nm. And now we have 2 summations. Solve them one after the other, because usually after writing down the first and using stuff you know, the second one is very simple. So let's do this. So let's have the m run and the n stays. So 1, 1, n, c, n, 1, 1, plus c2, 1, n, Cn1, 2, plus C3, 1, n, Cn, 1, 3. So this is just resolving here the summation over m. And now we already see C is antisymmetric in the lower two, so this term must go out. These terms stay. But now if we look at the structure coefficients we have, what are the non-trivial structure coefficients? We have C, 1, 2, that's this one, only has the 2 component, and that is 2. Okay? Then we have here the C1, 3, only has a 3 component up here, that's minus 2. And finally, C2, 3 only has the 1 component here, and that is 1. And all unrelated C's, all unrelated C dot 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 vanish. Now what do we mean by unrelated? Well, you see, because of the antisymmetry, for instance, this is the same as C2 to 1 if you add a minus sign here. And the same here. So those, of course, are therefore not 0, but they're not unrelated. They're related. But all the others are 0. So now if with this knowledge, we go here and we see we have Cn1, 2. So the only one with 1, 2 that doesn't vanish is this one. Okay? So that is a 2. This is a 2. But it's only a 2. Hang on a second. It's only a 2 if the upper index is a 2 as well. So in fact, if in resolving this sum, the only one that survives is C2, 1, 2, C2, 1, 2, because here we need the 2, but then we have to have a 2 here too. Then you have C1, 2, C2, 1, 2, C2, 1, 2 is 2 times 2 is 4, according to our insight here. Similarly here, Cn1, 3, the only one that survives is C3, 1, 3. So this is plus C3, 1, 1, because here you have C1, 1, 3. No, is that right? C1, 1, 3. No, there's a 3. I'm sorry. So there you have a 1, 3 there. That's this one. So you have to have the 3 up here and the 3 here. That's it, because it's the 1, 3, the only one with the 3 up survives, so 3, 1, 3. So this guy is minus 2 times minus 2, but that's also 4. So in total, we have as the 1, 1 component of the killing form, so this entry here, this is a number 8. That's it. So now you repeat this for these 7 more entries in precisely this fashion by starting with K1, 2, yielding this one, and so on, and you get the killing form. I think it's too boring to go through this here, but my assurance to you is that calculating the K1, the Kij's this way, one finds 2 things. A, K is non-degenerate. That means that the SL2C Lie algebra we're looking at is semi-simple. And I remind you that semi-simplicity implied that SL2C can be written as a finite direct sum of Lie algebras L1 to Ln that are each simple Lie algebras. Okay? And B is more like a side remark, and that is there's something else we can read of the killing form. Namely, I mentioned that before, the killing form K is also negative definite. So I hope I got the sign conventions right here. It should turn out to be negative definite. And no, it's not. Okay. No, the statement is it's not negative definite. It's not negative definite. Because negative definite means, only negative definite would imply that the Lie group over it, the Lie group we came from some time ago, the Lie group, capital SL2C, was compact, was a compact group. So that the manifold underlying as a topological space is compact, but it's not. So this is, group is not compact, and that's true. So SL2C is not compact, and K is not negative definite. All right, so we saw that SL2C is semi-simple. The question is it already simple? So is SL2C really still decomposable into simple algebras, or is it already just only one summoned? So the claim here is, yes, indeed, the SL2C Lie algebra is already simple. Not only semi-simple, is indeed simple. Now, what was the definition of a Lie algebra being simple? A Lie algebra L is simple. So this is a reminder. Lie algebra is simple if it contains no non-trivial ideals. And what is an ideal? So we also recall I being a vector subspace of L is an ideal of the Lie algebra L if, now this is a symbolic notation, if you take any element of L and you take the bracket with any element of I in the bracket with any arbitrary element of L, so that's obviously a set if I denote it like this, and if the result again lies in I. So if the elements in I's are so strong, you can think that even if bracketed with an L, you do not land outside I. You stay within I. That's an ideal. Okay, and of course I equals just the 0 in the vector space L always is an ideal, because 0 with something is 0, and I equals the entire vector space, in this case the entire Lie algebra, is an ideal of this Lie algebra, because L with L lands just in L. So these are called the trivial ideals. They're always there. If we require them to be absent, no Lie algebra would satisfy that, but simplicity just requires that there are no others than these two. So now how do we check this in practice? Because we have to show there are no such ideals. Well, consider a set I that consists of alpha x1 plus beta x2 plus gamma x3. So far arbitrary linear combinations of a basis, of our basis we have here. And well, we now try to restrict the alpha, beta, gamma such that we do not get a trivial ideal. Restrict alpha, beta, gamma such that we do not have a trivial ideal. So restricting them all three to be 0 would produce the 0 ideal. Not interesting. Not restricting alpha, beta, gamma, these complex numbers, not restricting them at all would of course yield any linear combination of these basis vectors, which recovers the entire L. So we try to find another restriction, and we'll in fact show that there is no other restriction. And that means there is no ideal. Well, let's look at this. So we take this alpha x1 plus beta x2 plus gamma x3, and we need to check whether whatever element in L we take, we get again an element that lies in here for suitable restrictions. But because the bracket is bilinear, it's in particular linear in the second entry, so all we need to look at in consecutive order is how this guy here, this general element from our would-be ideal I, how that commutes with the three basis vectors. because that tells us all. There's no need to look beyond the basis vectors, x3, comma, x3 bracket. So what we need to do, we need to calculate these brackets in order to get an insight. Now, okay, so I now erased it, but you remember that x1 with x1, well, that's 0 because of antisymmetry. x2 with x1 yielded the plus 2, I think. It's the plus 2. So we have here the opposite, so it's minus 2 beta x2. And the one with the 3 yielded the minus 2, but here we have the other order, is plus 2 gamma x3. So that comes directly from the bracket of these basis vectors we have. Now let's calculate this one. x1 with x2 we said was 2, so it's 2 alpha x2. x2 with x2 vanishes, and this is x2 with x3 yielded x1, wrong order, so minus gamma x1. And this guy here is x1 with x3 yielded minus 2, so it's minus 2 alpha x3 that was. x2 with x3 yielded x1, right order, so this is plus beta x1. So these are these brackets, and now in this case we can discuss this very quickly. Look at the right-hand side. So what we produce here, so that's this right-hand side here, what we produce consists of a linear combination of vectors 2 with 3, but this is 2 with 1, and this is 3 with 1. Okay? Now, if neither alpha nor beta nor gamma, which are the factors here, beta, gamma, alpha, beta, vanish. So they could be related, they could be the same, but if none of them vanishes, then what we got here is 3 linearly independent vectors on the right-hand side. We have 3 linearly independent vectors on the right-hand side of this equation. Well, but 3 linearly independent vectors, of course, produce, if I chose different factors here and I choose to put into the third and into the second entry an arbitrary linear combination here, so an arbitrary L, I would recover the entire L. Okay, so that means if I have restrictions here, whatever the restriction is, if not alpha, beta, gamma are 0, I recover all of the Lie algebra. So, but then that means that the I would be could only be the I could only be all of L. So it'd be a trivial ideal. Now that we don't want, so hence 1 of alpha, beta, gamma must be, at least one must be 0. And now we have to do a case-by-case analysis. Case alpha equals 0. Now let's assume alpha is 0. Now we set alpha to 0 here, that's our restriction, so it means our ideal just lies in the x2, x3 plane. Now if that is true, then in order to have an ideal, also the result must lie in the x2, x3 plane. But everywhere, for all these 3, but you see in the x2, x3, this gamma is in the way for this guy to lie in the x2, x3 plane. So gamma must be 0. In this case, it immediately follows that gamma must be 0. But also here, in order to lie in the x2, x3 plane, this guy is in the way, so beta also needs to be 0. Aha, so in this case, it follows that they all are 0, and that means that I just is this trivial ideal. Aha, so this case is excluded if we want to have a non-trivial ideal. Now, let's say beta is 0. Same game. If beta is 0, then the I must be just the x1, x3 plane or a subset thereof. And if we look at that, 1, 3, 1, 3, so this one needs to go. Well, that already goes. 1, 3, this guy is in the way, so that means we need alpha equals 0. And now we cannot immediately read off the other one. We have to now take seriously that we have beta equals 0, alpha equals 0. That means the whole result must lie in the x3 plane. Well, but in order to lie in x3, for instance, here this gamma is in the way because that gives you a contribution in the x1 direction. So in the next step, it follows that gamma equals 0. However, with the same result, I is trivial. And the last case, well, that's too boring to go through. It's exactly the same thing. I is again trivial. So the only possibilities we had, we started from here, I could be either the entire Lie algebra or it could be the zero vector space. That means there is no non-trivial ideal. There exists no non-trivial ideal I in SL2C, and that just means SL2C by definition is already simple. So it's not only semi-simple, it is simple. Okay, so that we just did for completeness. So now let's go to the roots and the fundamental roots. So roots and fundamental roots of the special linear group here of the relativistic spin algebra. Sorry, not of the group, of the algebra. Okay, so first we observe the following. From the commutation relations, let me write them down once more. x1, x2 equals 2x2. x1 with x3 is minus 2x3. And x2 with x3 is x1. So that's our Lie algebra in this example. And we observe, okay, so this is the algebra, and we observe that H being the span, the complex span of just x1 is a Cartan subalgebra. The Cartan subalgebra of L. Why is that? Well, that's since add the adjoint of x1 acting on x2 is, by the definition of the adjoint being just the bracket between x1 and x2, is 2x2, and the adjoint of x1 on x3, that's minus 2x3. And so we see we have a decomposition of the basis. That means that the basis, well, that L being the complex span of x1, x2, x3 is such that this spans the Cartan subalgebra, and these two are eigenvectors of the adjoint of every element in here. Well, every element in there is just a little h in H, but every H has, of course, the form psi times x1, where psi is a complex number because H is one-dimensional. So it's the Cartan subalgebra we have there. And you know that we decided to read this, this set of eigenvalue equations somewhat differently. So we have two, well, okay, so now we get a notation issue here, because so in the past what we did, we denoted these guys H1, H2, H3, and these E1, E2. Okay, well, let's stick with one type of notation, and maybe that even clarifies more the conceptual issues here by having to think about why the numbering is now different. So actually we have two functionals. One is called lambda 2 and the other one is called lambda 3, and they're associated to this x2 and x3. So in the past we called this E1 and E2 in the abstract theory, and then correspondingly we call this lambda 1 and lambda 2. Now we stick here with this labeling, but the key point is that each of these is a linear functional, so they actually linearly map the elements of the Cartan subalgebra into C. And of course, a linear map defined on a one-dimensional vector space is fully defined. So defined by, well, like any linear map, is defined by action on a basis. Now, in a one-dimensional vector space, the basis is just this. We define this to be 2. So this is lambda 2 on x1, of x1, not on, of x1. And here the lambda 3, also linear functional, defined by lambda 3 on x1 on one basis element is minus 2. So that means that the minus 2's here, this guy and that guy, we secretly, or not so secretly, think of them as lambda 2 of x1, and we think of this guy, we think as lambda 3 of x1. So it's the evaluation of these linear functionals at x1, which is the x1 from over here. Okay? Good. So this, if you compare this to the general theory, you know why we do this. And so, of course, we have lambda 2 and lambda 3 are therefore elements of the dual of the Cartan subalgebra, and they're called the roots. They are the roots of SL2C, and the entire root space we always constructed, in the general case, capital Phi, simply consists of these two guys. And you see we had the abstract result that if you have a root, then minus that root is also a root, and that is the case here. Minus lambda 3 is lambda 2. Okay, that's the root space of SL2C, and it's these particular roots defined on a basis like this. Now, we also wanted to look at fundamental roots. What are those? Fundamental roots is a set pi, which is a subset of all the roots, decidedly a proper subset, such that A, the set pi, is linearly independent, and B, every lambda in phi, so every root, can be written as follows. For every root, there exist numbers n1 to n dim. There could be 0. I think was to be positive, not negative. No, all right. So we could take n to the size of pi, and these numbers are integers, but they could be 0 because our notation of the integers included the 0. And there exists an epsilon, which is either -1 or +1, such that, and that's here the expansion, lambda is epsilon times the sum I equals 1 to size of pi, ni times pi I. So these ni's, so you can either have only non-negative coefficients, if you take all of this together, of the pi's, or non-positive coefficients, but you cannot have plus pi 1 minus pi 2. That's not allowed. That's this construction here. We discussed this before. And well, now in this case here, it's particularly easy. So here we choose pi to be, for instance, the root lambda 2. Because obviously the other root I get by this rule by just taking this to be 1 and this to be minus. And we could have equally chosen, that's a good example here, the choice of fundamental roots is not unique. We could have equally well chosen lambda 3 to be the fundamental root. But, well, we make this pick. This is the fundamental root. Okay, so, well, once we have the fundamental root, we can make the following check. We can look at the while transformations, which constitute the while group. And you remember that the while transformation, you have an S lambda acting on a mu, and the lambda can be any root, and so can be the phi here. And this was linear in mu, so this was mu minus 2 times lambda comma mu by lambda lambda times lambda. So this is decidedly linear in mu, but it's also decidedly nonlinear in lambda. This is the while group. And we know that the while group, that only plugging in fundamental roots here generates the entire while group. And the only thing we can do here is to consider S pi on pi. Well, yeah, so we could call this guy pi 1. So it's the first fundamental root. Okay, maybe that's silly. Maybe here it's clearer to say we take this fundamental root and we can act on itself. And we calculate this. This is lambda 2 minus 2, lambda 2, lambda 2 by lambda 2, lambda 2. And here, of course, this is the dual, by these brackets, I mean the dual of the killing form, restricted to the realification of the Cartan subalgebra. So K star is the dual killing form on the realification of the dual Cartan algebra. Okay, well, here lambda 2, but of course this is 1. This lambda 2 minus 2 lambda 2 is minus lambda 2. Well, indeed, acting with the while group on lambda 2 with respect to lambda 2 produces the other root, because we know action of the while group or repeated action of the while group on the fundamental roots generates the entire root space. So it's clear that our general theorem here applies to the while group acting on the fundamental roots generates, the set of fundamental roots generates the all the roots, the entire root space as expected. Well, if it didn't, it showed that we calculated wrong. So, and finally, what we can write down is, of course, the Dynkin diagram. Well, first the Cartan matrix, maybe. Well, that's particularly simple because we have just one fundamental root. The Cartan matrix is a matrix, but it's a 1-by-1 matrix, and so it has only a diagonal element, and we know this diagonal element is always a 2, because we're dealing here with a simple Lie algebra. So that's where it pays off that we check this. And the Dynkin diagram is also particularly simple. The Dynkin diagram we have here is, of course, just a circle, because the Dynkin rules instruct us to draw a little circle for every fundamental root. Well, the fundamental root space is just one element. That's the Dynkin diagram. And so that means that SL2C has this Dynkin diagram, but this, so it's not a 0, it's a Dynkin diagram. And that is, of course, in the classification of the Lie algebras, this is the space A1. It's the space A1. So we found at the end of this road that the Lie group, the Lie algebra of the big SL2C Lie group is A1, in the standard classification. Okay, so now let me, so the example of SL2C is finished, but I would like to give you another example, and that is the reconstruction of a Lie algebra from its Dynkin diagram. So far we came from the group, we went down to the algebra and then to the Dynkin diagram. Now we go the opposite way, well, at least from Dynkin diagram to the Lie algebra. But now we won't start with this one, this is too boring. We consider the Dynkin diagram that looks like this. Let's consider this guy. So how do you reconstruct from this the Lie algebra? Well, obviously, you have two fundamental roots. So you have a fundamental root space that consists of two fundamental roots, because for every fundamental root, we have a circle. So these are the fundamental roots. Aha. Now, we have something on top. We have one bond between the two. But so that means that the bond number n1, 2. So say this is the root 1, this is the root 2. It doesn't matter because the diagram is symmetric. But the bond number n1, 2 is 1. Now what's the bond number? Well, if you remember, the bond number ij was Cij, Cji. So C12, C21. And be careful, the Cartan matrix entries, they're not symmetric. They're not symmetric because Cij was 2 times k star of pi I pi j by k star of pi I pi I. That's the Cij. You see it's linear here in the j, but the pi I appears 3 times, so it's definitely not linear. So this is this guy. Well, we further found that these guys are less than 0 for I non-equal to j. So the off-diagonal elements of the Cartan matrix are negative. Now, okay, so that will play a role in a second. And we also found that the Nij was equal to 4 times the cosine squared of the angle between the ith and the jth fundamental root. Aha, so that means in our case we have 1 equals n12 equals 4 times the cosine squared of the angle between our 2 fundamental roots. And this angle, of course, referred to this k star on the realification. And I maybe also, well, yeah, let me remind you that pi was a proper subset of phi, and phi was lying fully, of course, in the real span of pi, so that was in HR star, which was defined as the real span of pi, and that of course lies fully in H star, which is the dual of the Cartan algebra, and which we said was also spanned by pi. So maybe you want to note these inclusions in evaluating what we do here. So if I speak about angles, I of course need a bilinear map. Well, I need a metric even, and because we're semi-simple, it's a non-degenerate metric and so on. And I have this here. And we also found that although the killing form may be a non-positive definite or indefinite even on here, or the dual of it, on this realification, we saw it's even positive definite, so we can definitely define these angles. Now, of course, we can take the square root here with some care. So this is 1/2 equals, yeah, but then the cosine, it's the absolute value of the cosine of the angle between the two guys here. And if we think about the cosine here at pi half, or 90 degrees, then, only need to go to here. There are actually two places where the absolute value of the cosine is 1/2, and that is at 60 degrees, and that is at 120 degrees. Okay? The question is, which of the two is the right solution? So by taking the square root, we lost this. But now you see, we need to go back to the Cartan matrix, since 0 is greater than C12, and C12 is K star of pi1 with pi2 over K star of pi1, which is positive. We saw this is positive. That means that the K star between pi1, pi2 is negative, so the situation is not 60 degrees, where the projection is positive. The situation is 120 degrees, where the projection of one on the other is negative. So that means we have that the angle between the two fundamental roots, and that's of course a general rule because the off-diagonal elements are always less than 0. Whenever coming from a Dinkin diagram, you have to decide whether you have an angle less than 90 degrees or greater than 90 degrees. You pick the one greater than 90 degrees. You must pick it because of this sign. And so this is 120 degrees. Okay, so this means that in this two-dimensional real vector space, it's two-dimensional because pi has two elements, our fundamental root space. This means we have the following picture in HR star, the realification of the dual. So let me draw two axes. I can choose one of the roots to be represented by, well, this point. This is 1, 0. And then the other one must be at 120 degrees. So let me put it here, for instance. It doesn't matter. You could rotate the whole thing. But that then needs to be, if this is length 1, minus 1/2 square root 3/2. Let me think. This is squared is a fourth plus 3/4 is 1. Yeah, that's right. Okay, so we can take this here as the other root. Okay, so these are the two fundamental roots. Now, so this is pi1, and this is pi2. Well, at least it generates this. Well, you see pi1, pi2 are well, yeah, it's fine. It's these functionals. So it's the space of the functionals. It's two-dimensional. So now, by repeated action of the while group, so repeated action of the while group, we should recover all the roots. So what do we do? Well, we start with this one. We already know that S pi1 of pi1, we calculated this before, gives you minus pi1. So you definitely can get from this guy here, you get this root here, which is minus pi1. Okay, so what else can we do? We can act with the pi1, S pi1 Y transformation. We can act on the pi2. Now that's interesting. Let's write this down. This is pi2 minus 2 times, by definition, pi1, pi2 by pi1 times pi1. Now what does that yield? Well, that's pi1, pi2. We already know what happens between pi. So this is again K star, K star. What happens between pi1 and pi2? Well, it's 120 degrees. Well, this is represented here, so we can simply take these components. We project this one to that one. That gives you a minus 1/2. So this is pi2 minus 1/2 over, well, this one has length 1, pi1. Okay? But this here, of course, in total is just a minus hang on a second, minus 1/2 plus, no, and there's a 2 in front. I forgot the 2. Okay, so then in this case it's just a +1. So it's pi2 plus, okay, the notation is not so good. Well, you can do this elementary arithmetic. This is pi2 plus pi1. Aha, so I start from here and I take this one here, so I go here and I land here. So the next one we get here is this guy here, Huh? So that's this calculation, and this one here is that calculation. Aha, so we got these two. So now you can imagine, I'm not indicating this in detail, you can imagine by repeatedly acting, for instance, by acting on this result again with pi1, well, let's do it. So we take pi1 and we act on the result on pi2 plus pi1. You can calculate what you get. So this is pi2 plus pi1 minus 2 times, oh dear, okay, so this is pi1 comma pi1 plus pi2 divided by, divided by pi1 times pi1. So what is this? Pi1 with pi1 plus pi2 is the projection of this one and that one, and that yields you plus 1/2. So what you get here is pi2 plus pi1 minus, and then there's a plus 1/2, so minus 1 over 1 pi1 minus pi1. Oh no, by this you go back to the pi2. Okay, so that didn't yield anything. So this one gets you here. Well, then you have to act with this on that and so on. Anyway, what you get if you do repeated actions here, I don't want to go through it in detail, you get 2 more roots. You get this one and you get that one. And any further action of the while group will only permute these roots amongst each other. So what do we have? We have roots, a root space of size 6, and we have a dimension of h which is 2. How do we know this? Well, this we know because the dimension, the complex dimension of h is certainly the complex dimension of its vector space dual, because it's a finite dimensional vector space, but this is certainly the real dimension of the realification. You can see this from here, right? So this has 2 elements, this has 2 elements. The real basis has 2 elements, the complex basis has 2 elements. So the complex dimension is the real dimension, and that is simply 2. And we know that the sum of these two, that the dimension of the Lie algebra is the dimension of, sorry, this is without these guys, just the dimension is 2, is the dimension of the Cartan subalgebra plus the size of the root space, which in this case is 8. So we already found that the dimension of this Lie algebra is 8. So from this it follows the dimension of whatever Lie algebra is represented by this Dinkin diagram is 8. Okay, and we constructed the entire root space. So, having reconstructed from this Dinkin diagram for A2, that's obviously the A2 algebra in the standard classification, the root space, which we found was a 2-dimensional real space, or at least the realification of the dual of the Cartan algebra, was this root space here with these 2 fundamental roots, 1, 0 and minus 1/2 and square root of 3/2. But by repeated action of the while group, we also got 1/2 square root of 3/2, as well as minus 1/2 minus square root of 3/2. Then this one, which is 1/2 minus square root of 3/2, and of course also this one here is minus 0, minus 1. 0. That's the root space. So from here we go to here, and now we want to go from there to the full algebra. So we want to really understand the commutation. I said commutation relation. That's a terrible mistake, because this is no representation. This is just the Lie bracket. It's abstract. It has nothing to do with any commutation. It's more like a habit to say this. And their structure coefficients here. So if I chose a basis xi, xj, there'd be structure coefficients I, j, k here. And we already saw that in this case here, I and j run from 1 to 8, because it's an 8-dimensional algebra. So this we already completed, and this step will now perform. So how do we get these commutation relations? Well, one thing we know is this is by construction a simple Lie algebra. We already identified the Cartan subalgebra. It's the one spanned by these two fundamental roots, or where all these roots lie. And so what we definitely know is that we have two of the basis vectors, h1 and h2. They constitute the Cartan subalgebra. So if you write here the span over C, then we have here the Cartan subalgebra spanned. Okay, fine, Cartan. And then we have E1 to E6. We have 6 vectors. Those are the eigenvectors corresponding to these root eigenvalues. And we know that we can choose such h1, h2, and e1 to e6 such that we have the add of some h acting on e alpha is lambda alpha of this h, evaluated at this h, e alpha, where the lambda alpha are these roots in the root space, okay? But thought of as these functionals, and alpha runs from 1 to 6. Aha. So in particular, we can choose a base, can evaluate this on the basis vectors. Add h1 of e alpha is lambda alpha of h1 e alpha, and add h2 e alpha is lambda alpha of h2 e alpha. And now these are concrete numbers, and these are the numbers that appear here. So this guy here, so this whole guy, is the pair. Let's say it's associated with the first vector here. I can make that choice. It's lambda 1 of h1. And the second member of this pair is still lambda 1, but evaluated for the second basis element I chose here for the Cartan subalgebra. So actually taking this into account, we have, so this is one thing. And the other thing is that this add, so I should write here implication arrow like this, but this adjoint action is nothing but h1 with e alpha. And this adjoint action is simply h2 with e alpha, okay? And okay, and we know that we have here the e alpha, so we read off from here, we read off that from up here, C, so I now look at the structure coefficients. This one is the structure coefficient C1 alpha, and you see the only, this can be expressed as simply a factor times the E alpha, so we have C alpha 1 alpha is, well, it's lambda alpha of h1, and down here we have C2 alpha, alpha is lambda alpha of h2, and here there's no sum, okay? So this is really the alpha alpha, so that runs from alpha from 1 to 6, alpha from 1 to 6. So we get 12 structure coefficients. 12 of the structure coefficients we have, because of the antisymmetry, we have actually okay, so there's a potential danger. The potential danger is that I labeled this as 1, and that corresponds to the H1, and the alpha also runs from 1 to 1, so you could think that 1, 1 is 0, but that's not true. So we should call these guys 1 bar, 2 bar. These are other ones than these, otherwise we get into trouble with our index notation, but you see it's not so much of a bother. So H bar, 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 okay, bar, bar. So we have a bar over here. So 1 bar is not 1. It labels another basis element. So these are 6 plus 6 makes 12. And because of antisymmetry, these are already 24 of the structure coefficients, structure constants. They're coefficients too, but let's say structure constants of the Lie algebra, which we recover directly from the root diagram. Now that's not all of them. You see, I mean, what about the 1 bar up here, and what about alpha beta down here? So how do you get the remaining ones? Well, in particular, we see that coming directly from the definition of this Cartan algebra, we only learn about commutators that contain an element of the Cartan subalgebra. But we certainly also want to study, so also want, okay, so we already got more. Sorry, let me add this. We know that if we have H1, H2, and we have a simple Lie algebra, we know that the Cartan subalgebra is always abelian, so we also learn about the coefficients C1, 1, 1, 2, all of these, but the non-trivial ones are these here. And let me write an I up here if I mean all 8. So these guys are certainly 0, so that's another 8 non-trivial ones, 16 in total, and so on. Okay, fine, so we learn these two, but this is all commutators that contain at least one element of the Cartan subalgebra. So, but we also need to learn about expressions like this. How do the e's amongst each other work? So we know how the e's work with the h's, we know how the h's work amongst each other. All that remains to be clarified is how the e's work amongst each other. And by the way, of course, everywhere here, I strictly speaking, in our notation, I mean this double Lie bracket. So please apologize whenever, depending on context, this is this, so this is that thing. Okay, but obviously it doesn't seem that at first sight from the Cartan construction we get information about this. Well, but of course we have the Jacobi identity, so the idea is use the Jacobi identity to learn the following. We need to use some h to learn something, so take h, one of the h's, so let's call that with a capital index a, so a then runs from 1 to 2, we're here safely or firmly in this basis representation, ha, and we then take the bracket with an e alpha and an e beta. And so we take these nested brackets, alpha beta runs from 1 to 6, and we hope to learn something. Of course we do, because by use of the Jacobi identity, this is minus, now we cyclically rotate through, is e alpha, comma, bracket, e beta, comma, ha, close bracket, minus, open bracket, e beta, comma, ha, comma, e alpha, close bracket, close bracket. So this is simply the Jacobi identity. And of course, this gentleman here, for instance, we already know what that is. This is lambda alpha of this HA times E alpha. Okay. This here is minus, because you could flip this, is minus lambda beta of the same HA. And so therefore, what you learn here is, times E beta, of course. So you can have this alpha beta, there's a minus here, there's a minus there. This is just a number once it's evaluated. The bracket is bilinear, so you can pull it out. This is plus lambda beta of HA times the commutator E alpha, comma, and all that's left of here is the E beta. And back here it's similar, but you get in E beta, E alpha, well, let's write it down. It's minus lambda alpha of HA of E beta, comma, E alpha. But of course, the E beta, E alpha is just minus the E alpha, E beta. So in total, we have lambda alpha of HA plus lambda beta of HA. Bracket is the factor that goes with E alpha, E beta. Okay, so what does that tell us? Well, that tells us that this bracket E alpha, E beta is also an eigenvector of the HA. But if this is an eigenvector, okay, well, so therefore we have that add HA acting on this commutator E alpha, E beta is lambda alpha HA plus lambda beta HA times E alpha, E beta. That means E alpha, E beta is also a root. Okay? So hence E alpha, E beta is, well, I say it's a root. Well, it's a root if the sum, you see, you could write the lambda alpha plus lambda beta, you could take the sum, considering them as the H star elements, and only after taking the sum in H star, you act on HA. This can either be a root with corresponding to the root lambda alpha plus lambda beta, if there is such a root. Okay, so let's look at the diagram here, over here. So assume we call this guy, let me get some color. So it's important to not get confused here. So, so this here corresponds to the root lambda 1. But associated with this root is, of course, the E1 is the eigenvector to which the lambda 1 of H is the eigenvalue. And similarly, let's take this guy here. So this guy here, this is lambda 3, say. And of course, this is associated, but it's not the same as a vector E3. So now the question is, what about the commutator of E1 and E3? Well, if you want to write down that commutator, so maybe so if you now wish to have that commutator E1 with E3, okay, then you know it's a root. You take this guy, lambda 1, you add it to lambda 3, and you land exactly here. So this is lambda 1 plus lambda 3 applied to some h, if I act on here with some h from capital H, and then I get exactly this guy back, E1, E2. But you already know that the E1, that the vector that yields this factor here, which is now yet another color is maybe in order, which corresponds to that guy. So this is, of course, lambda 1 plus lambda 3. Okay, this is lambda 1 plus lambda 3. You already know what that guy is. That must be the root we found before. So E1 and E3 must be the E2 that corresponds to this root. Okay, so we found that E1 and E3 is E2 because these two sum up to lie here. So this is one type of relation you get. Now there could be two other things happening. So this is the case where lambda 1 plus lambda 2 yielded another root. Okay, so we could say this in generally, the commutator E alpha with E beta equals, now we have three cases, and we just clarified case 1, that is in E gamma, if lambda alpha plus lambda beta, the corresponding roots, add up to the lambda gamma. Okay, that's this case. So, but what if they hadn't added up to something that already exists? So take, for instance, this lambda 1 and this lambda 2 here. Well, their sum, so I refer again to this rule that you get the sum, their sum would lie here, but this is not a root. So in this case, where this is not a root, the result is 0. I should say if this sum here is in the root space, that's the right formulation. And it's 0 if the sum lambda alpha plus lambda beta is not in the root space and is non-zero. Then we put a 0 there. But then there's a third case, that is, you take, for instance, this root and you take that root. So you take these opposite roots, but of course the corresponding eigenvectors, they're not linearly dependent. They are E1 and E1, 2, 3, 4, E1 and E4, you know, they're linearly independent. The roots are not, but the corresponding eigenvectors are. What happens if the sum of the roots is 0? If the sum of the roots is 0, what can happen is that this guy is an element of the Cartan subalgebra. Now you do not immediately know which one, but by repeated application of what you know using your brackets, you'll find out. And an example we had before that is again simpler as this one was SL2C with this Dinkin diagram, and this root space, we didn't draw it at the time, but we know that the root space is one-dimensional, so that's H, well, the realification is real one-dimensional, and we had only one fundamental root, that was this one, okay? That was the fundamental root. At the time it was called lambda 2. Of course, by action of the while group, we get this guy here, we get the opposite, we get minus lambda 2, which you could get by S lambda 1 acting on lambda 1. Okay, so we saw all of this. And we saw that this one plus this one is 0, and indeed we had that the eigenvector corresponding to this one, so this was the lambda, we then called lambda 3, that the eigenvector of this one with the eigenvector of that one, that yielded x1, and that was in the Cartan subalgebra. And that's an example for this third case up here. And so this way, first evaluating what happens on the Cartan subalgebra by definition, and then using the Jacobi identity and making this distinction of cases, you can recover the entire Lie algebra, the commutation relations, that is the Lie algebra, not commutation relations, I correct myself again, the Lie bracket relations, which only if it's a representation would appear in the form of commutation relations of, say, matrices or linear maps. The Lie bracket relations are recovered fully from the root diagram, and the root diagram comes directly from the Dynkin diagram. So the Dynkin diagram really contains all the information about a simple Lie algebra. See you next time. Thank you.